into what we're doing. So this is sort of an interesting point in the class because structural induction is so important. It's one of the differentiators of our class. And in fact, as you know, there are paths for the CS major that don't require this class. For example, there's a path through engineering where you take engineering math, and some mathematicians take combinatorics. But it turns out that in CS 330, and also most computer scientists do structural induction on a weekly or daily basis. And so it's incredibly important to know about it. The other thing that's incredibly interesting, I think, is that for me, my experience when I was taking math courses, say in grad school, is that you go to some party and they say, what are you studying? And you say algebra. And they're like, oh, that's terrible. That's like what, 5th grade? And you say, I'm studying geometry. And they said, oh, what's that? That's like 7th grade? Because most things have a version that is for pretty young people. And maybe that's why I chose to concentrate in topology, where they don't have an analogy of that in high school. But one of those things is structural induction, which is not particularly advanced mathematics, but it is something that you will never hear them teaching in high school or first year math classes, and incredibly useful too. So let's dive into it and talk about it a little bit. It's really cool and really important, and we want you to know it. I will start by sharing my screen here, and then we'll go to the document camera a little bit later. Let's see, screen, podcast. All right, please let me know, can you see the tablet and also hear me?
Yep.
Excellent. Okay, so these notes are already on the web. I'll annotate and mark them up a little bit as we talk about it. As I mentioned, the reading in the Cliff Stein book is quite good, and I hope we're recording. Let me just double check that. Yes, according to my phone, we're recording, which is good. All right. So structural induction is a nice way to prove things about computational processes that have data structures in them. So recursive lists, trees, that kind of thing. But let me just motivate this by talking about where is functional programming and Lisp and things like Scheme. Where are they used actually today? Well, they're used a lot, actually. So the Mapreduce paradigm, you already know about map. Reduce is also called accumulate. It's in the book, but we'll go over it a little bit on Wednesday. So Mapreduce is a parallel and distributed programming model, and it's used widely. Invented at Google, but used in Facebook, Yahoo, Microsoft, Amazon, all over the place. Cloud computing in general, I'll give you a lecture on Mapreduce. I think it's lecture maybe 13 or 12 or something like that. Another example would be a company you may never heard of, but one of the most successful startups out of MIT ever, other than core memory and quantum computing. So it's called Ita Software. So as you may know, the airline reservation system is a legacy system, and Sabre covers all airlines except for Southwest and JetBlue. And there's an interface to it entirely written in Common Lisp, over 500,000 lines of code. This is acquired by Google in about 2010. Now it's Google Flights. So the entire thing's written in fairly functional version of Common Lisp. But also TripAdvisor is implemented in Common Lisp. Lisp is used in AI to prototype new languages. Computer-aided design. Basically, programs that manipulate other programs frequently have this as a basis. And even closer to home here, our very own TA, head TA, undergraduate TA, Andy Zhang, is using Scheme to design proteins and antibodies because his interests are at the intersection of computer science and biomedical therapeutic design. So in all these cases, it's mission critical to know that your manipulations are correct. How do we know that? Well, we have induction, but we liked something that was a form of induction that was particularly applicable to data structures. So today I want to talk about essentially reasoning about list structures, not just writing code. You know, how can we do induction on list structures, particularly structural induction, and we'll even talk about induction on trees, although most of that I will leave to section because I wanted to have plenty of time for things like questions. So let's go back to recalling lecture 6. And we had lists, you make them with cons, head, and tail, and we know what proper lists are. The head is the first, the tail is the rest, and so forth. And we can define a lot of procedures to manipulate lists, and you've already been doing that in section and in assignments and so forth. But here's our function copy here, which copies a list. And you know, how do we know that this actually works, right? So, you know, we have a lot of questions we might want to ask about this thing. How do we prove it's correct? And of course, we sort of have this idea that what it does is it takes in a list like this. L is bound to a list that looks like this in box and pointer diagram notation. And we have 1, 2, 3. And as we work through this, we find it returns something that looks like this. It returns a pointer to this guy here. So it's an exact copy of the list, and using functional programming, you can't actually tell these things apart. If you could, you know, basically functional programming is a way, ensures that these are identical in terms of how they print and how they behave. Now, if I could change one of these, like change the 2 to be a 15, and you could do that with side effects, then the two things would be actually distinct mathematical objects. So we'd like to know that this behavior that I've just sketched here is actually correct. I mean, this is a diagram, this isn't a proof. How do we know about that? I'd like to show you a couple of proofs of that, but you can see this can be non-trivial. Like, what about reversing a list, right? You've already addressed this in your short assignments. It's trickier in some ways. You can't just interchange the arguments to cons. You know, what's the running time of reverse in terms of n? Can you write a faster one? And can you prove it's correct? So even if you think that for copy, this is obvious. And by the way, if you do think it's obvious, congratulations, you're becoming a computational scientist or mathematician, because people who are experienced can look at this and say, that looks pretty correct. But for now, we're going to prove it rigorously, but you can probably see for reverse, especially when you get some variance on that, it's somewhat more difficult. So let's build a basis for thinking about that. Now, one way you could start to do this is by thinking about induction, right? List and recursive list processing, we could start to do induction on these things. So the thing is that how would we go about showing that for all lists, copy L is equal to L? But this is a different kind of induction. If you look at this here, there are no numbers. We've only inducted on numbers before, right? And there are numbers. There are numbers which are the, you know, the heads of these, or the cars of these lists. But really, it's on list objects that don't have numbers per se. So we have to think about how to do that. So we've been doing induction on the integers, and we can make that work. We can basically recast our problem to be induction on the length of the list, and that's going to be an integer, absolutely. So the length of the empty list is 0. The length of the list, you know, x like this is 1, and so forth. And then we can do a proof by induction. And I'm going to go over to the document camera now. I'm going to do this proof for you, which I think that you'd be able to do too, especially given this hint. But what I want to say is that after that, I want to show you how to do it by structural induction, and it will be similar, but quite a bit cleaner. And then we'll try to do some examples that illustrate the advantages of structural induction, which is the way basically to do induction over things like lists. So give me a minute and I will head over to the document camera, get set up there, and we'll do this on paper because it's math. All right. All right, I hope I'm back. Can you see the document camera? Can you hear me?
Yes, you're good.
Good. Glad to hear it. Okay. So, you know, I've tried to sort of set this up to be sort of reasonable here. We have our induction recipe, at least part of it. We have copy over here so we can keep in mind of the code. And we have the idea of inducting, well, not directly on the list. We have the idea of inducting here on the length of the list. All right. So let's just do a proof like this. And then this will be a proof by regular induction. This is not structural induction because it's induction directly on an integer here. All right, so let's start out and do it. We'll follow the induction recipe. I'll say claim for all lists L, copy of L is equal to L. How do we show this? So proof by induction on n, which is the length of L. And we have a statement that we're trying to prove. And the statement is going to be copy is equal to L for any list L of length n. And our base case will be the empty list. In other words, n equals 0. And in this case, what do we have? Well, copy, and basically we know in this case L is the empty list. So copy of the empty list must be the empty list by the substitution model. So you apply substitution, and you can see that that has to happen. Okay. Now, one thing I want to mention is that I've given you the fancy version of copy here, which is map. So it's a little hard to see that. Let's instead use this version, which I think will be a little easier to see. Because in order to really prove this, you have to go down into map, which will be a little more tedious. So we want to get to something that's a little bit non-trivial, like our example here. But because we're doing this in this context, I actually just want to use this simpler version of map that I should copy that I showed you before. Excuse me while I put the paper clip on here. This was somewhat more facile when I practiced it, but. All right. So if I've done this correctly, you can see copy here. So why is this true by substitution model? Well, because here in the code, which I just showed you on the last page, we check if it's null and return the empty list. So the base case is relatively straightforward in this case here. All right. Now the induction step is going to work like this. So first we need an induction hypothesis. We say assume for any list L of length n that copy L equals L. And I'll label that clearly as the induction hypothesis like that. Then we have to just show it for a list that has something else glommed onto the front of it. Need only show for any list, I'll call this L prime, of length n plus 1, that copy of L prime is equal to L prime. All right. So how do we do that? Well, let's just look at the substitution model to begin. And first we know that null of L prime is going to return false. Why is that? Because the length of L prime is equal to n plus 1, which is greater than 0. So we don't have to do with the base case. We're in this part of the code here where we're consing ahead on the copy of the tail. Okay. So now we have to expand this here, copy this cons head onto the copy of the tail. Let's just look at the inner part for a minute. So let's look at copy tail of L prime. Well, we want to know what this is equal to. How do I reason about that? Well, the length of the tail of L prime is going to be equal to the length of L prime minus 1, which is n. So that means that copy of tail of L prime is just equal to tail of L prime. How do we know this? By the induction hypothesis, which is clearly stated above. So we're almost there. Now we've already figured out what this is equal to here. This is equal to tail of L prime. Now we just have to expand the entire form. Therefore, I'll write thus: copy of L prime is going to be equal to, and here I'm just using substitution model, going to be cons head of L prime onto what? Copy tail of L prime. And that's just going to be equal to cons head of L prime onto tail of L prime. And that follows by the above reasoning here. But that's just equal to L prime, and we're done. All right. Any questions on proving that for all lists L, copy of L is equal to L using induction? Any questions before I go on?
I think there's some questions in the chat, and I have a similar question. What would be the advantage or disadvantage of doing this proof on like using strong induction and having the induction hypothesis be assuming it works for all k less than n?
I don't need it. It would be fine.
Okay.
So I mean, I don't see an advantage in this case, but if you would assume that, it would go through. You're just assuming more than you need to.
Why don't you need to assume that?
Because I only need to show it for one more. Like if I was somehow putting together lists that were smaller than n, I would need to do that for sure. And we need to do that later in this lecture. For this one, I didn't need to. But there wouldn't be anything wrong with doing it. So I only needed to go from n to n plus 1. But if you were somehow doing some kind of operation that had a lot of smaller lists, then that could indeed be an issue. Other questions? You think you could do a proof like this? Getting comfortable?
Maybe.
Okay, well, let's go on. I was going to write this. I'm going to try showing this instead because it's a little dense and I want you to see. I mean, it's not dense like it's really bad, but it's a little dense in the sense that I want you to see kind of how I chosen to word it. So let's try this. Okay. So the key thing here is that what we did is we inducted on the length. And mathematically, in terms of computer science, it's kind of a kludge. We didn't need to do it. It's kind of inelegant, it's an extra thing. So induction is supposed to be defined on any inductively defined set. So the natural numbers are defined by 0, and the relation or the function, the successor of x is equal to x plus 1. And these things generate the natural numbers in some sense. But similarly, we can inductively define the set of lists. So it's defined by the empty list and the way to get something that's 1 bigger, namely cons xl for any expression x and any list L. Doesn't matter what it is. So we can do a more direct proof, and this is called structural induction. And there's a recipe for it like this, which we'll talk about, and we'll do some examples. So again, you do induction on a list. The statement is some claim about the list, like written P of L. There's a base case, which is usually the empty list. And there's an inductive step here. And basically, this is to prove that for all L prime, that if the property, all lists L prime, that if the property holds for L prime, then it holds for a list where you've consed S onto L prime, no matter what S is. So in other words, we assume that the property holds for L prime and show it holds for the result of consing S onto L prime for any S, no matter what it is. So it's a little bit mind-bending at first, but very powerful. So we induct directly on the structure of the list with no need to have a middleman of the integers for the length. Now, here's some things to remember. And this is the part that I really felt I wanted to, have you see the writing so I can mark it up. So induction on the integer length is just normal induction. It's not structural induction. Now, either one could be a proof, but if we're teaching you a technique, if you give a proof like that and it's not structural induction, it's not correct for this class. So think about it. I know some of you have interest in biology. If I ask you to solve a problem by PCR and you end up solving it by NMR, that could be a perfectly valid thing to do, but it's not answering the lab question, right? So induction on the integer length is normal induction, not structural induction. Here's some other things. So we're assuming the induction hypothesis for any list L prime. And we show the inductive step for any S that you're consing onto it. So S can be absolutely anything, and cons S L prime, all those things are just one element longer. So this is one reason I showed you so many examples that were similar to this. So we induct structurally on L prime and universally quantify over S. That means for all S. So again, this concept, which comes up again and again, of treating two variables differently, L prime, the list, and S, the thing you're consing on, it's very similar to things we've seen before. When we had times 1 AB, we inducted on B, but let A be any number. So we had to show the property held for any A. And similarly, when we proved things about rational numbers, yes, S is any object, any expression actually, because it's an expression that returns a value. Similarly, when we proved that the square root of 2 was irrational, remember we basically inductively searched over the rationals like this. And we inducted on Q, the denominator, but we let P be anything at all. So in other words, we had a property that had to be true. And this is something that we'll do repeatedly. It's very common in mathematics, but that's why I picked those two examples, one easy and one hard in some sense, in order that you could see kind of how this would really work. Like how would we really deal with two variables at once? Now, here's the trick that will make our proofs much, much easier. And it's just a notation for proofs. We won't use it anywhere else. So in order to do proofs, I'm going to denote the value of cons SL as S dot L. Formally, we say this: cons SL returns a value, and in proofs, and only in proofs, it's just a thing for proofs, we'll write that value as s.l. And this will make our proofs a little simpler. Okay, so this is our idea about how we're going to do structural induction. But I have to give you an example of how we're going to do this. And the example is going to yet again be our example copy. So I want to bring back copy here, our poor little folded up thing. And as you can tell, I'm not going to be getting a part-time job as an origami person. All right, so there's our copy over here like this. And we want to do structural induction to show that copy works using this new proof technique. So I'll just do that right here. All right, so we don't need the s.l, you know about that. I'll just leave up the, example here. I'll leave up the recipe for structural induction. So now I'll say claim. All lists. Same as before. So we'll revisit our proof of copy by induction on lists. We'll prove it this time by structural induction. Proof by structural induction. And I have to say the variable on what? L, which is a list. And my statement will be simply copy L equals L. And my basis will be L equals the empty list. And we have similar reasoning to before. So what's the reasoning again? We're going to say copy of the empty list is equal to the empty list by substitution model. And why is that? Because null of the empty list is equal to true. So that's similar to what we had before. Now the induction step. So again, I need an inductive hypothesis. So I'll say assume copy L prime equals L prime. And I'll label this as the inductive hypothesis. I'll even underline it. Then what do I have to show? I have to show that copy of s.l prime is equal to s.l prime for any s. Okay, so how do I do this? Well, first of all, it's not null. And why is that? So null of s.l prime, remember s.l prime is just cons s onto l prime, is equal to false by definition, because the object here contains at least s in it. So it's obviously not null. So now coming back here to copy, we're obviously in the cons clause of copy here, and we have to expand that and figure out what's going on. So therefore, we're looking at something like this. We're looking at copy s.l prime, and that's going to be equal to, just expanding this, cons head s.l prime onto copy tail s.l prime. And this just follows from the substitution model. In other words, I took this expression here and I substituted in the actual arguments for the formal parameters. So that's fine. But this is simply equal to cons s onto copy L prime. What's the reason I could write this? What reason would I put down in a proof on the right-hand side?
Substitution. Well, by induction hypothesis.
Actually, not both good guesses, but not quite. This is from the contract for lists, but it is kind of substitution, right? But this is really from the list contract. That's the definition. Like if you Cons S onto L prime, and then you head it, you get the head. If you tail it, you get the tail. S is anything. Note here, any S, any object. The list contract, let's write that down here. The list contract we went over in lecture 6. So, contract. So if I take any two objects and I say cons x, y, that's a y, that's an x, and then I car this or head it, I get back x. And if I cooter this or tail it, that's a y, I get back y. And the other part, of course, is about the null list. This is from lecture 06. Good. Is that a question, or is that just some line noise in someone's house?
I believe someone's unmuted.
Not a problem. I do that all the time. All right. All right, so this follows just from the list contract. So it is a form of substitution, but really substitution doesn't let you expand this unless you have the contract. So I would say list contract for that. But this is just equal to cons S onto L prime. Why is that? Why can I write that statement? What would be the reason I write in the right-hand column?
The inductive assumption.
Inductive hypothesis. That's by the inductive hypothesis. Stated exactly here, right? And then this is equal to S dot L by definition. I'm done. So that's a proof by structural induction. No funny business about having to induct on the length whatsoever. Induct directly on the structure of a list. Sorry, was there a question?
Well, okay, I just wanted to ask, where did you apply the list contract in our case? I can't really see it.
So how do we get from this to this, right? So all I did here is I said that head of S dot L is equal to S, and tail of S dot L is equal to, oh, sorry, this is tail. I think did I make a mistake here? I just typed that just incorrectly. Thank you for catching that. Yeah, so all I've said here, no, I'm good. So all I'm saying is that, let's just write it in here where we can see it all at once. So how do we know that head of S dot L prime is equal to S? And how do we know that tail of S dot L prime is equal to L prime? That's the question we're trying to resolve. Because this is head of S dot L prime, which I claim is S, and this is tail of S dot L prime, which I claim is just L prime. Are you following me?
Yeah, is it because S dot L prime is the cons of S and L prime, and then the head of that would just be S, and the tail of that would just be L prime?
That's exactly right. So let me just write that down in case anyone was confused. So say cons S onto L prime is written in our proofs as S dot L prime. Now, the reason I mentioned this contract is that all data structures, basically all code has a contract for how it works. And our code just here says how cons works, and that was in lecture 6. So that's the name for this fact, if you will. Was that helpful?
Yeah, thank you.
Good. Any other questions about copy by structural induction?
Could you explain the difference between L and L prime? Like what exactly is L prime representing here?
Well, it's a list. I just found that some students like to have it be different from the one up here. You could have used L, but some students, especially when starting out, and there's nothing wrong with this feeling, by the way, because it's a feeling, is they're a little uncomfortable with the idea that the statement is the same thing as we're assuming. And so what I did is I just assumed it. This is what we actually proved, but I just assumed it for some arbitrary list L prime. So one of the things about mathematics is it's a lot like when you are naming the arguments to your procedures, right? You can pick any name you want. Now, of course, you'd be wise to pick a reasonable name, but you can pick any name that you want. So the smartass answer is I just picked L prime because I wanted to. But the slightly better answer is I just tried to pick something that was different from L. So someone who was worried about assuming what we proved, which is not actually what we would have been doing, would be comforted by having a different variable name. Does that help?
Yeah, so they're just basically the same thing, essentially.
Yeah, I mean, it would be perfectly valid proof to make them the same thing, and mathematicians would do it that way. But here I just kind of wanted to have a different name for it just to make it go through. But you can unify them if you want.
Okay, thank you.
Absolutely. Any more questions about this proof? All right, so I'm going to show you a couple of more things. Now, remember, here's our paradigm here. I'm going to leave this one for section, but here's a fairly general way of testing membership in a list. Again, it's a kind of recursive process on list structures. So member tests whether thing, which is an object, is contained in the list. Very useful. Now, the only things to mention here is that equal is a fairly general way to tell if two things are equal. It basically means, do the things print the same way? So it actually would say that two lists, 1, 2, 3, and its copy would be the same thing because they ask, does it print the same way? And this is something we could prove actually either way. So what we can do is we could prove that member always returns true if the thing, the object here, is actually in the list, which is what we would like. So I'm going to let you do that in section and meditate on it a little bit. Or to do yourselves, I'll leave the recitation structures to think about whether that's worth doing. And the main reason is that I think that while that's an interesting example, I would rather show you about trees and how we can use structural induction on trees. But by the way, the proof for member is actually in the lecture notes, which I think is, a pretty cool thing. Okay, so let's see now. All right. So I want to think about binary trees next. So we're going to have our structural induction recipe here, which is pretty cool. And I want to start making trees like this. Right, here's some code to make trees. And so these aren't balanced binary trees. They're trees that look something like this. Right, you might have a tree that looks like this. Maybe you've seen trees before, but in this class, we're going to prove things about them and write some quite interesting functions. Binary tree might look like this, only left and right branches at every node. So I'll give you the constructor for these later, but the way that you would think about a thing like this is you would have a left, which is head, a right that's tail. So you might imagine implementing trees as con cells. And we'll test whether or not we're at a leaf because it'll be an atom, i.e. not a con cell. So what I'd like to do is do induction over binary trees to prove that functions that operate on trees are correct. So intuitively, a leaf is going to be a tree of depth 0. It's pretty reasonable. And any other tree has a depth 1 larger than the max of its left and right subtrees. And the trees don't have to be balanced, as you can see from this example here. So a little more formally, if you will, we'll say a leaf is a tree of depth 0. And if, say, T1 and T2 are trees of depth D1 and D2 respectively, then, and I'll use a constructor here that I haven't shown you, but it's pretty easy, make binary tree T1, T2 is a tree of depth 1 plus max D1 and D2. Okay, so depth of trees is going to be like length of lists. And it lets us map induction over trees to induction over the natural numbers. And recursion is the key here. Doing this iteratively would be a total nightmare. You probably would go blind trying it. It's just not the thing you want to do. So you need recursion here. So down here I have a little procedure called count leaves that works like this. And it counts the leaves in the tree using basically the scheme version of this mathematics here. Now, a little thing just for you to make sure you're kind of on the same page. So why do we have a 1 there if a leaf is a tree of depth 0? Is that right? Got a 1 stuck in here. Does that make sense to everyone? Go
You
ahead.
have to count like the original one, right?
Yeah, that's exactly right. So we're counting leaves, not depth. And you've seen some things for counting depth, so that's why it's super important to have the 1 there. So this guy is going to, we think, count the leaves in the tree here. Okay. Now, and by the way, I want to mention that these are already on the web. So the proof for member, which I believe only uses regular induction, is on the web, and the other proofs are on the web typed up as well. Now I'm going to start doing some proofs here, but let me mention that a thing I'd like to do is abbreviate count leaves by CL. So if you see that, that's what I mean. And of course, we could do that by saying define CL to be count leaves, and it would be correct. So we could prove that count leaves is correct. We could do that by inducting on the depth, and we know what the depth is, and we could do a totally normal induction proof. Now, this is not structural induction. We can do it to see what it looks like, and I put it in the notes for you. But I'm going to skip ahead to structural induction, which is a really nice way to prove this. But the full proof is in here using standard induction. I do want to make some comments about this. So you can look at that proof. We might do it in recitation to compare the two. But let me tell you the following. If we did this proof by standard induction on depth, as are in the notes, we could look at that proof carefully. And there'd be lots of talk in that proof about trees of depth k less than n, and trees of depth n, and so forth. In other words, it would have the depth in there as an explicit natural number that we'd be inducting over. So it doesn't have to do that, is the point. It's just a naming convention. So we can completely rewrite that proof in terms of leaves and subtrees. Okay, in English, leaves and subtrees, but plural of leaf being that data type. And depth never needs to be mentioned. So a good structural induction proof doesn't need to mention k, which are the size of the subtree, or n, which is the size of the tree you're trying to prove something about at all. And instead, we induct directly on the structure of the tree. Again, induction on the integer depth is normal induction, not structural induction. And similarly, let me just say that, in scheme, if we were to do this, rather than, mathematics in some sense, when we say cons x onto a list, and we get back x dot L, we never use the length of the list L. It never has to reference nor increment any indices like I plus 1 or anything like that. And our SI proof for copy doesn't mention the length of the list at all. And here I'm going to do with you the proof of correctness for count leaves, or CL, by structural induction in the same way. Okay. So how would we do this? So a little definition will be useful here that is basically implicit. You may not need this, but I think it will be useful. So definition, let T be a tree. So I want to talk in the proof about left and right subtrees, and I just want to be really clear about what they are. I think they're intuitively clear in some sense. Then the value of left of T is called the left subtree. And similarly, the value of right of T, remember these are defined in these constructors here, is called the right subtree of T. We need that definition there. And let's bring this back just so we can remind ourselves the structural induction recipe for trees. Now, I haven't really shown you what this means for trees yet, so I'm going to develop it on the fly, but we want to get to understanding this. So I'm going to develop this kind of like I did for lists and then show you the recipe afterwards. So I'm going to do a proof and then kind of generalize it. All right, so how do we do this? Claim. If T is a tree, then count leaves of tree T is equal to the number of leaf nodes in T. Okay. Proof by structural induction. Let's do a base case. Well, as you might expect, the base case is T is a leaf. Well, what happens here if it's a leaf? Well, it's a leaf, we return 1. So in that case, count leaves of tree is equal to 1. And we get that by substitution model. This is clearly correct because leaf is true, and clearly there's just 1 leaf in the tree. So base case is pretty straightforward. What about induction? So we need an inductive hypothesis as always. So we'll say assume count leaves applied to a tree S is correct if S is a subtree of T. And this will be my inductive hypothesis. So for any subtree, I want to assume that for any subtree of T, that count leaves is correct on that subtree. Now, obviously this can be viewed as a form of strong induction because the subtree S might not have depth, just 1 less, or it might. Now, if I can show that, assume that, then I really need to show the following. That I need only show that count leaves applied to T is correct when T is not a leaf. So T is not a leaf, so clearly the leaf predicate is false. And we now have this expression here, this plus count leaves left tree and count leaves right tree like this. So how do we think about a thing like this? So here's how I would do this. So again, let's just underline our induction hypothesis here. Count leaves of S is tree when S is any subtree of T. So now we're expanding this form here by substitution model, and we have that count leaves applied to tree is equal to plus count leaves left of tree and count leaves right of tree. Okay, this is pretty nice. So let's examine this expression a little bit. So the first thing is that by definition, this beast here is a subtree of T, because that's how subtrees are defined. And then this creature here, this is also a subtree of T. So left T and right T are subtrees of T. But by the induction hypothesis, count leaves is correct on any subtree of T. So this is correct. Induction hypothesis. And this guy here, also correct. The induction hypothesis, which of course is stated right here. So this is what we want to have happen here. Clearly, if the left subtree has had its count correct, and the right subtree has had its count correct, we return the correct number of leaves by adding them up, and the proof is done. Okay. All right. So these proofs are very short, even for a very complicated function, which is kind of nice. And I have more to say on this, and I want to generalize it to a general recipe for you. But let me ask you, do you have any proofs, any comments on the proof, or questions on the proof about our argument that count leaves is correct, proved by structural induction?
Could you maybe go back to the inductive definition of what a tree is?
Sure. So,
Or
What
like
was
it
it?
was on a little like side sheet, like
here?
yeah, but it was on the right side.
On the right side. Oh, that was what we're going for. So that was a structural induction recipe of how to do structural induction, but we don't, only now can we actually address that.
Oh,
So I
we're-
want to take this proof, which is correct, I claim, but I would like to take, we can have a debate about that, and we should. I want to take this and then generalize that so something that'll work on any trees. But we'll definitely come to that side sheet in a minute, but I have to generalize this to get to it.
Okay.
Yeah. Other questions? So let's do the requested generalization, which I think will help in some ways. So again, we have everything here except how to actually make the tree. So I need to do that. So I have to say define make binary tree to take in a left and a right, and I do cons LR. So that's the part that I need to actually make this work. Now, at this point, we can talk about what is our general recipe for structural induction. And let me just derive that. So we'll say structural induction recipe for trees. So we have to have what variable. A tree, say T. And then we have a statement, which is some claim about T, a property of that tree. P of T has to be true. And the base case, which is a leaf. And the inductive step, basically what we're going to do here is we're going to prove for all subtrees S and R that if the property holds for S and the property holds for R, then the property holds for the result of making a new tree with S and R as the left and right subtrees. So again, it's very similar to induction before. We assume the hypothesis holds S and R, which are subtrees, and we need only show it holds for, in scheme, make binary tree S and R. So that's our recipe for structural induction. And as promised, it's typed up a little more neatly in the notes, which are here. Okay. Does that help with the last question?
Yes, thank you.
Sure. So now we know quite a bit about trees and doing inductions on them. Okay. So our structural induction proof for count leaves followed this recipe. And again, induction on the integer depth directly is normal induction. It's not structural induction. But the benefit is that our proof is very, very simple. Like there's a lot of definitions here, but basically the base case is trivial because it's the empty list. And then all of a sudden this comes together with sort of a very brief argument. And yeah, this is typed up for you. Please take a look. And this is how we would do structural induction in this case. Okay. Now, some things you might ask. What about trees that aren't binary, that are n-way trees, like trinary or quaternary, or I'm not sure I have all my ordinal numbers memorized, but 5-way or 6-way trees are trees that have different branches. Can we do that? And that essentially is part of short assignment 8. And we'll talk more about it in section probably. But there's also a corresponding notion of depth. You can do induction the standard way, or if asked, you can do structural induction on that. But that would be a thing to generalize and think about. So our big lessons for today are structural induction. For lists, we do induction over length. And for trees, we do induction over depth. But we can do this directly on the structures themselves. And we have a recipe for lists and a recipe for trees as an exercise for you in the notes. They're actually the same recipe, just specialized for things that look more tree-like and more list-like. Now, there are a couple of more things I would love to be able to do. But first, let me ask you, do you have any questions on structural induction, anything I said, any of the examples today that would be useful to go over? Please ask.
I have a question. Could you please go over the difference when you say normal induction and structural induction? I kind of get confused sometimes.
Absolutely, a very good question. So first of all, I will go over it, but do take a look at the notes afterwards and see if they make sense. If they don't, send us a message, we'll try to clarify. So if you only have standard induction, then you're doing induction, and you have a list basically, then you're basically doing, your choice is basically to do induction on the length of the list. So you have this data structure called list, but then you have to keep saying, and its length is n, or its length n-1. So you're doing induction directly on the length of the list. In structural induction, you don't do that. You do induction directly on the structure itself. So instead of saying, maybe it's worth writing something for this. So normal induction, we have a list of length n, induct on L. Structural induction, we have a list L. We have a way to get one more, which is s dot L. So we induct directly on L. There's no mention of N anywhere in here. And similarly for trees, we could have a tree of depth M, and we could induct on M to prove something about it. In structural induction, we have a tree S and a tree R, and to get one bigger, we make, for example, a binary tree out of S and R to get one more. So basically, we have this technique where we can go from a data structure to want something that's just a little bit bigger and induct directly on the object. Here we have a left and right branch. We can make a new one, and we can induct directly on the object instead. So in some sense, structural induction is more natural because we are working on sets that are inductively defined. So the basis of normal induction is that we're inducting on the integers, which are defined by 0 and the relationship successor of x is equal to x plus 1. Here our inductively defined sets are either lists or trees. So in the case of lists, our inductively defined set has a base case of the empty list, and then we do cons x onto any list to get x.l. And that's an inductively defined set. Similarly for trees, our base case is a leaf. And then we can get a new one by saying make binary tree out of two subtrees, S and R, to get a new tree. And when you think about them, it kind of makes sense here. I mean, here we have a subtree S and we have a subtree R. We proved that the property holds for this for S. We proved the property holds for R. That's done. When we make a new one here, a new tree like this, we merely need to show that if the property holds for S and it holds for R, then it holds for make binary tree, where we put those two things together. So the key thing is that in these proofs, there's no mention of the length, n. There's no mention of the depth. There's no mention of any integers that correspond to these things. And it's kind of nice in a way because these, of course, have different lengths. So you're inducting directly on the structure. So the analogy I would make is that in some languages, when you have linked lists, you have to have a pointer, you have to have an index, and you have to go down the list and keep track of how long the list is. In Scheme, none of that exists. You just have, give me the first, give me the rest, and you can go down the list until you get to the end. Similarly, when we do structural induction, we just have a list, and we can have the head or the tail. Those are the only operations. We can do all our everything based on that. So you're inducting directly on the data structure without having a middleman, which is the length or depth of subcomponents of the list. So take a look. Does that help?
Yes, very much. Thank you.
Sure, happy to engage. This is a deep question. We'll go back to it many times. We'll have assignments on it. We'll go back to it in recitation. Happy to discuss it. So ask if you're confused. Take a look at the notes. See.
Thank you.
Sure. Other questions?
When is normal induction sufficient to prove things? Like it seems like the case where you're inducting on like the depth or length of a list might not be sufficient to prove the property. What are examples of that?
Well, there's nothing you can prove by, it's like the distinctions we said before. There's nothing you can prove by strong induction that you can't prove by weak induction. And there's nothing you can prove by structural induction that you can't prove by normal induction of either kind. So it doesn't give you more power, but it makes the proof substantially easier and especially easier to read. So it's kind of like the analogy I mean, pick your favorite language, which of course has to be Scheme, but supposing arguendo was something else, you know, C++ or ML, I don't care. Pick your favorite language. Someone asks you, and I'm being a smartass here, couldn't you just do all this by writing assembly code? Well, sure, you could, but one is more powerful. So we think of this mathematically as expressive power, how easy it is to do the proofs. Does that help?
Yeah, thank you.
Yeah, but I think you're asking a deeper question, which is, are there proofs that cannot be proved by induction? This is a much harder thing for me to give you a definitive answer on, but yes, there are many proof techniques and induction is only one of them. So there are things that induction doesn't work for, but we'll never ask you to prove by induction something that can't be proved by induction. However, we might ask you, can you use induction? Probably it'll be false if we can't prove it by induction. So there's a large class of things that induction applies to, and they're basically inductively defined sets. Natural numbers, things the same size as the natural numbers, lists, trees, basically all data structures. And now you know how to prove your programs are correct for data structures, and hence the term structural. All right. Happy to take questions. I'll stay around afterwards, but I wanted to show you one more thing. So let's go back to our question about the contract for cons. So we can cons x onto y. And the contract says that if we take the car of that, we get x back. And if we take the cdr of that, we get y back. And of course, there's something about null lists in there too in the contract, but I don't need that for this little digression. So one of the things you might have noticed about it is I'm usually pretty adamant that we have to know how to build these things. And you were very nice not to press me on that. And I said, well, in some sense, what cons does, or might do, is it makes a cons box like this, and it makes this point to object x, or its value this point to object y, and it returns a pointer to this thing. And in fact, you can implement cons that way, and we even could show you, some more scheme functions and primitive functions that would let you do this. And this is how programmers often think about cons. But in a way, my appeal to this diagram as the storage model of cons was kind of shockingly non-specific for this class where we're supposed to be able to implement everything ourselves. In other words, in Feynman's words, what I cannot build, I cannot understand. So do we really understand this? So one of the reasons we have contracts is that it should be fair if cons as an implementation satisfies this contract to change the implementation to something else. And one reason I was a bit laissez-faire about this was that you could actually implement cons without any storage model using only higher order procedures. So in other words, when I came to lecture 6, I could just appeal back to lecture 4, where I gave you higher order procedures and define cons that way. So I'd like to leave you with an exercise for you all to think about that's pretty useful. It requires only knowledge of higher order procedures and substitution model. But the reason it's important is that everything we've done for data structures is basically based on cons. So you can think of them this way, that's perfectly fine. But to stretch your brain mathematically a little bit, imagine I define cons and car and cdr like this. So I could say define cons to be lambda x, y, lambda m, x, y. In which case I claim that car could be implemented as a function of one argument, z. What does it do? It takes z and it applies it to an anonymous procedure, lambda pq, and returns p. So there's a programming part to this and then a proof part. So the first programming part, if you will, or code part is, how would you define cdr? And then the second part is show using substitution model that the contract holds for this implementation of cons, car, cooter. And by contract, I mean this specification here. So the reason I wanted to show you this, it's a classic exercise in the lambda calculus, but this is why I didn't get particularly exercise showing you really a very new thing for data structures, which was the ability to make objects like this. And the reason was that we already knew how to make it. You already had the skills to implement cons, car, and cooter just using procedures. So as excellent practice, try to do cooter yourself, given these examples, and using substitution model, try to use that on these procedures to show the contract holds. And if you can do that, this kind of completes a key point about programming languages, mathematics, and computer science, is that to implement data structures, you don't need pointers. You don't need a storage model. You actually don't need anything but lambda. No pointers, no storage model. All you need is lambda. So in some sense, in our context here, lambda is a constructor. Sort of the ultimate constructor. You can construct any data structures. So lambda plus higher order procedures is going to give you data structures. And this was the key insight of the mathematicians who developed the lambda calculus. Alonzo Church, Turing worked on this too, so Hilbert, is they realized you could build any kind of structure you would want. Now, practical note, this is all true, but there may be more efficient to implement it with a storage model. But this has exactly the same semantics as our contract for cons. And you can show that, prove that using substitution. So this is one reason why I was happy to show you the storage model here. And we can even talk about implementing this. But it wasn't really a new thing because something with exactly the same behavior, i.e. semantics, could be implemented just using higher order procedures and our favorite friend for making procedures. So this is a little bit mind-bending. Don't think you should understand it immediately, but take a few minutes to see if you can understand why this implements cons, car, and cooter. See if you can write cooter yourself, given these examples for cons and car, and then for each of them, prove that the contract holds for this. And if you've done that, you will have implemented data structures, eschewing pointers, eschewing a storage model, only using lambda as your method for constructing them. And the reason this fits here is that we've just done some very sophisticated things, relatively speaking, with lists and trees. So we've introduced trees, and now we have all the mechanism to prove that functions that iterate or recurse over trees are correct. Similarly for lists, we have all the techniques we need to show that data structures involving lists are correct. And all of those structures are based on a constructor called cons and his family of contracts to take them apart. Cons can be thought of operationally as a storage model. That's totally fine. Also, you just think of it in terms of the behavior, which is this contract. But I wanted you to see that actually we can implement that just based on what we knew in lecture 4, namely higher order procedures. And if this seems a little mysterious to you, take a look and see if you can get your head around it. It's a really great exercise. And really, this is the kind of logic that underlies mathematical computer science just as much as several other key branches. And I wanted to show you to kind of cap out our knowledge of trees, given the trees are made with cons. Okay. So we're just about at time. What I'd like to do is to stop the recording, and I will stay around in this Zoom link, and I'd be happy to take any questions. Let me go here and stop the recording so we don't have all those things. Let's see, where are both?